Hello everyone, I'm Michele Portolan from TIMA Laboratory in Grenoble, France, and I will present you our paper about dynamic authentication-based secure access to test infrastructure. We outline first, we'll start with setting the problem and show what is our use case about the secure access, and most importantly, to point out the problem and the potential about having test and security coexist in the same system. Then, after a fast state of the art about the 1687 standard flow and the usual security issues and solutions that are found in it, we will propose our security solution based on a legacy flow and going through several steps until obtaining a fully automated flow for which we'll show some experimental results. And finally, we'll draw some conclusions and show some perspectives that are opened by our work. What is the problem of access and security? Is that technological trends are pushing tests always further. Something like 0 DPPM means higher test coverage. New usages and standards like ISO 26262 mandate online testing, meaning that the system and the testing infrastructure must be accessible also during lifetime. The widespread usage of IP-based design means that now we also have a third-party IPs to test together with our own hardware. And to answer these problems, solutions like 1687 provide an easy and rich access. So we might think that everything is fine in an ideal world. But what about the security of these new systems? Is opening everything up really a good idea? There are several test-related security hazards. First of all, the tap can be a backdoor because a malicious user can go and through the tap basically access everything that is inside the system. There are several examples of JTAG and the tap being used to reverse engineer or just simply to change the access rights to a system. And just thinking of putting some static protections is not enough, because if we have attacks like made in the middle, it means that if someone is sniffing about the transactions that are going through the system, our secret key will simply be copied by the man in the middle, and they will gain access for basically every other system behind. This means that we must never use the same information twice. And this changes a lot in terms of testing, where I used to generate a pattern set once and for all, because the pattern, if we have security information inside this pattern set, the man in the middle will be able to access it and extract the information from this pattern set. So how we can integrate test and security? Custom solutions, of course, do exist. One of the strong points of the test setting is that solutions are always found one way or the other, but they are limited to special cases, and they usually require an important user's intervention. What we would like to show in this paper is to try and obtain a completely automated and transparent flow where a user will be able to access a user, thanks to some security credentials, can request access to a system and obtain it based on his credentials. And the ADA tool will be able to understand and case by case open or close these secure connections in a completely automated and transparent way from a user point of view. Because we must remember that especially for online testing, the user is. So what is the current status of this? First, of course, we have the IJ tag, the 1687, that is used a lot in the new systems, thanks to two main novelties. The first is the introduction of dynamic scan chains that allow to change the length of the system, and so to boost accessibility and performances. And the other is in the interactive functional execution, meaning that we can write and receive data from the system. Problem is that the 1687 is difficult to integrate with a legacy flow that is depicted here, where we have this duality about smart generation and fast, let's say, dumb execution, where we just all the intelligence is put in the generation phase by the EDA tools to obtain a pattern set, but then it's just applied as fast as possible to the systems without thinking about what is going on. The problem in this system is that the execution engine is the automated test equipment has no knowledge of what inside the system. So it's not able to differentiate if this user is trying to access all access system or a secure portion of it. In the same way, there is no return path for the data, so it's extremely difficult if we define some authentication, some dynamic scheme to obtain the answer for the system. That's why in TIMA we developed MAST, that is a dynamic interactive functional engine for 1687, which presents a full interactive flow. So it's something that is able to execute any algorithm on any topology with any interface. And so we decided to try and adapt it to the problem of secure access. The idea of MAST that instead of making this duality of generation and application, we'll have a first step of elaboration of compilation, where we'll take the algorithm that we want to express and we'll execute it directly on the test host, where thanks to a configuration file that could be, for instance, in ICL if it's 1687, we have the knowledge of what happens inside the system. So we know at each moment, we know exactly what is the status of the system under test, and we are able to configure its SIBs, its dynamic elements. And as we're doing it on the fly, we are also able to open a bidirectional data path between the algorithm and the system. So we solved the two issues of the legacy flow of 1687. As I said, security solutions for 1687 do exist, and the main idea is to exploit the dynamic chains, so the SIBs, to lock away sensitive information, and then to modify the opening of the SIB to assure security. The first solution and most known is the locking SIB, where the idea is to have a secret key that is hidden inside the system. So the different bits are spread around inside the system under test in a way that is difficult to obfuscate it. And the LSIB will open only when all the bits are in the right place. This is the good idea, but the problem is that this type of attacks, this type of solutions is prone to attacks from man in the middle, because somewhere inside the pattern set, there are the keys. So through some reverse engineering, it's possible to understand where these key bits are. And once the key has been retrieved, the secret is not possible anymore. So there has been some proposals of different types of locking SIB, in this case the secure SIB, S2IB, where the security does not come directly from a hidden key, but there is a secure chain that is added to the system that is made by an external controller that is able to decide the opening or the closing of the secure parts. So this allows for more complex and more secure authentication schemes. The problem is that this controller is outside of the 1687 flow, so must be handled separately. One example of the usage of this secure SIB is the fine-grained access scheme, that is a challenge response scheme. So the idea that each time a user needs to access some secure connection, will will have to answer a challenge that is generated by the controller. So this allows to have custom access permissions, but the problem is that authentication can be extremely long because each time if there are multiple secure areas, the users will need to ask for authentication for each one of these areas. So there will be a need to store a lot of secret keys in memory, basically one for each possible configuration. An evolution of the VGA scheme is the segment set authorization key protocol that is also on a challenge-based scheme where the user has this SSK key that is connected with a circuit key, but the main point is that the challenge will depend on a configuration also. So the challenge that is generated inside the circuit, thanks to SSK, is merged together with the configuration access, so which SIBs needs to be open. And it is this configuration that is used as an answer to the challenge. So the two parts, the user and the circuit, will obtain the same response, that is a combination of the unique challenge that is being generated inside the circuit and the configuration that has been asked by the system by the user. And this response will be used to unlock or know this SIB. The advantage is that there's a predefined segment set. So as the configuration, it's possible to ask to open or close several SIB at once. So there is just one need for an authentication. There is no need to authenticate separately each one of SIBs. As the key generation is done dynamically, the memory footprint is reduced. And also it's possible to add some user ID to the configuration and the SAK so that it's possible to certify the user identity for the circuit. The hardware implementation, as I said, it follows the idea of the secure SIB. So a crypto processor is added to the controller so that that then will handle the generation of the configuration of the different SIBs through the secure chain. And this is an approach that is compatible with standard hash function and other types of ciphers. So how do we put everything together to obtain a secure 1687 flow? In a legacy flow, we will have a pattern set that is obtained from an EDA tool. And on this, around this pattern set, we will need to wrap the authentication steps to open and close the different secure systems. And this wrapping is done directly on the test environment. So it means that we need a big user intervention because it's up to the user to add this authentication. This is done completely outside of a standard flow, so you cannot exploit standard tools and the help from the ADA tools. And also it completely depends on the host. It's not portable. If you're doing it on an ATE, if you're doing on an embedded processor, if you're doing it from a desktop connected with an USB to JTAG converter, each time your authentication changes. So this is the legacy solution that is usually done now, that is used to validate this solution, but this is also what is blocking a widespread adoption. A first step will be to make authentication exploiting 1687.1, so using PDL1. It means that the authentication algorithm can be written using the PDL1 overlay layer and added directly into the PDL1 execution. So the main advantage of this solution is that it's becoming portable, because as you're relying on your 1687 ADA tool, you're not dependent on the execution host anymore. Problem is that still you need a lot of user intervention, because the user who needs to define the wrapper. So the user also must be trusted, must be inside the trust zone. And what about the scalability? Because basically you will have to replicate this wrapper each time you have a different secure section. A complete authenticated solution is to extract remove the responsibility of authentication from the user and put it directly inside the ADA tool. So what we did is to define, to take the user outside of the trust zone. So the authentication in the SSH protocol is directly used by the ADA tool, by the MAST tool. Each time the user tries and asks access to a secure section, an SSH authentication is triggered based on its certificate. If the authentication is successful, the SIB will be open and the execution will continue. Otherwise, it will be stopped. As I said, the main interest is the user is outside of a trust zone, so it doesn't know exactly what. He has no direct intervention on authentication. He can only provide his own certificate. And moreover, this is directly implemented inside the ADA tool. It's completely scalable because we can have as many users as needed can go and make this authentication thanks to their own certificate, and it will be up to execution tool, to 16887 tool, to handle this authentication. How did we implement it? We've exploited a callback model that is inspired by the new solutions of the 1687.1. So you can, there is in ETS a special session, the special session 104 about 1687.1. You can look at it if you're interested in the details of how this callback model works. The idea is that by implementing it inside our MAST tool, we are enabling the tool to be enhanced with security protocols coming from the outside. So we can imagine to have third-party providers providing secure access inside the chips and providing their own callbacks that will be added to our system. So we're generating a trusted environment where each third-party vendor will provide the protocol for the ADA tool and the authentication credential to his customers. To prove it's to demonstrate the working of the system, we had an experimental setup where we have two users, in this case user 1 and user 3, who need to access secure portions inside a system on chip. While we also have a third user, in this case user 2, that is a standard user because it just needs to access non-protected areas. The three of them are executing their own PDL and relying on the MAST tool to make the retargeting and access the system under test. And we provided a callback, so a plugin for the SSH authentication that is provided to the MAST tool. What are the results? If we look at the first solution where the authentication is directly written inside the PDL1, we can see that each PDL here with, put in yellow will be executed, and before and after execution there is a step of authentication that is depicted in green. So in this case we can see user 3, user 1 will execute their code thanks to authentication, and then user 2 will be able to access. Why we'll need this sequential execution? Because the authentication is outside of a dynamic topology that is handled by the tool, so it's outside of a standard flow. So we need to execute these two pieces of PDL and of authentication separately before being able to run the normal system. On the other hand, if the authentication is done inside the MAST tool, what we can observe is that the authentication is done just once, thanks to the common authentication of SSH. So we have already a gain about the authentication because the MAST kernel is able to authenticate both I1 and I3 in the same moment. And then once the authentication is done, the execution can be done in parallel. So we're gaining a lot of time thanks to the concurrent execution of the PDL1 code. And in the case there is an error about the authentication of one of the three of the system, so we can see that an error is raised by the system, but execution is not completely halted. It's only the unauthorized PDL code that is blocked, but the rest of the system remains operational. This is also an advantage over a completely sequential solution where an error will cause the halt of the whole system. So what will be the conclusions and perspective of the system? We show that test and security have completely opposite requirements, but still there is a strong demand for their coexistence. In this paper, we show that it's possible to have a solution that is both secure and automated, and which is completely transparent for the user perspective, meaning that the same code will be portable and will be executable regardless of it being in a secure or in an open access section. And moreover, everything is completely integrated into the standard flow, which is a huge boost for adoption and for portability. As future works will extend to other type of authentication schemes, and also for adding the support for encrypted vectors, like for instance from stream ciphers. And more importantly, we exploit the fact that everything is inside a standard 1687 and even, I would say, 67.1 flow to integrate multiple security approaches and nested one inside the other. Because in a real situation, in a third-party situation, you could have different parts of your system that are protected through different schemes, and you will need to access them at the same time, even if they come from different solutions. So with this, I finished. So thank you very much. You can ask any questions through the ATS system or directly contact us by email. Thank you very much.